So the last thing we saw was the Archimedes principle concept. Archimedes principle was the main idea that you saw there was the buoyant force is equal to the weight of the fluid displaced. Right? Buoyant force was equal to the weight of the fluid displaced. That's what you saw. Now before I go into this, okay. And we also went through those equations. What is the weight of the fluid displaced? It is the volume of the fluid displaced times volume of the fluid displaced times density of the fluid displaced times gravity. You see those equations? That's a buoyant force. Now we were discussing about the ball. So when the ball is floating on water, that is how it floats on water with a little bit of the ball submerged. So what is happening over here is the buoyant force, the weight of the object. The weight of the object and the buoyant force are actually equal to each other because they are already in equilibrium. It is not sinking any further, nor rising. So therefore, the weight and the buoyant force are supposed to be equal. So the weight of the entire ball is equal to the buoyant force. The weight of the entire ball is equal to the weight of this much water displaced. So that's a concept that you should know in Archimedes principle. Don't memorize any other equations. You should know the main equations. Let me list the entire equations down. All the equations. You can actually put that on your note card, which will also be useful for the rest. Okay? What's the first thing you did in this chapter? What's the first thing you did in this chapter? Density. All right, so we talked about density is equal to mass over volume, which also means mass is equal to volume times density. Right?
Yes.
So we did that part, and then what did you do after that? After the density concept?
Pressure.
Pressure. We did pressure is equal to force over area, which also means force is pressure times area. So we went through the pressure concept. What's the unit of pressure?
Pascal.
Pascal. And you can also use PSI in case you want to just compare pressures, but the SI unit of pressure is Pascal. Okay? And then we did the pressure in fluids. What's the fluid pressure? What's the pressure as you go down in a fluid? What is that equation? What's the pressure in fluid?
P equals F1 divided by A1 equals F2 divided by A2.
No, not that one. Pressure in a fluid as you go deeper and deeper. What's the pressure in a fluid formula?
P atmosphere.
No, not
P
that.
F equals height times density times gravity.
Height or depth times density times gravity. Check and see if you have that. Yeah. So pressure offered as you go down in a fluid is the depth you go times the density of the fluid times gravity. What's the absolute pressure? What's the absolute pressure? What's the real pressure as you go down in a fluid? P atmosphere plus the PF, which is H rho F G. This is the absolute pressure, means the real pressure. So if you're going down so many meters in a lake, the real pressure there is whatever is already on the surface plus by the fluid. You get it? What else did you do after that? After going through the fluid pressures and all those things, then what did you do?
Hydraulics.
Huh? Hydraulics, which is what principle?
Pascal.
Pascal's principle, which says what? the pressure is transmitted in a fluid. That means F1 over A1 is F2 over A2. That is Pascal's principle. The force over area on one section of the pistons is equal to force over area on the other side, because pressure is transmitted. The same pressure is going everywhere. It's the same pressure that's going everywhere in a fluid. That is Pascal's principle. And after Pascal's principle, what do you do? Before we started Bernoulli's principle, we did this. Which is the volume per second. So how much fluid flows from one place to another place depends on the area and the speed. But if the area is changed, then the speed changes accordingly. This is the equation of continuity. The equation of continuity, which is a requirement for the Bernoulli's principle. That's why it is given earlier. So this is A1 V1 is A2 V2, which means if there is less area somewhere, are you writing it down?
Yes.
I guess, yeah.
If the water is moving, in the moving section, wherever it's moving at a certain speed, you're going to have the same pressure. You're considering a tube now. It's not like a lake.
Okay, but if there was a lake where like there's an undercurrent, I guess, you
Yeah.
could go down farther.
Yeah.
Without it.
That's the point. Yes. So if there is an undercurrent like this, the pressure there is lower. So in case you get into that place where there is an undercurrent, the pressure from below will suck you in and let you go through it. In no time you'll be somewhere else. Get it? So why you're getting, sucked in, most of the drowning is because of this. Most of the drowning is because of this. You think the river is normal and all that. Suddenly, there's an extra pull from below, and you're not able to take it. And so it gets suddenly missing. That's because you have got pulled into the undercurrent. So you're going to the low pressure area. To come from there to a high pressure area is tough. It's tough. Yeah, that's a good question. All right, so A1 V1 is A2 V2, so that is the equation of continuity. Wherever the fluid moves fast, the pressure is low, right? And what did you do after that is? What is the Bernoulli's principle? So as V increases, pressure decreases, right? Wherever the V is high, the pressure is low. That's basically the idea of Bernoulli's principle. We didn't go mathematically into it, but we just need the concept. And we did multiple examples using Bernoulli's principle, like a curve ball, and then tennis, golf, ping pong, what else? Ships colliding, airplane wing, bird feather, bird wings, all of them. They're all Bernoulli's principle related. Okay? In high winds, how the roof is getting pulled out. That's Bernoulli's principle. So there's a lot of Bernoulli's principle action that is actually taking place, and you should relate it to that. So as soon as you see something strange, you should, okay, is that because of some physics principle? Yeah, it is definitely related to some physics. That's why physics is kind of everywhere. So you will see it, and you'll understand, okay, that's the reason they're having this. Okay? Just when we asked a question. Related to Bernoulli's principle, that is. All right. So as the speed is higher in any place, the fluid pressure is going to be lower. Okay, that's Bernoulli's principle. And then what do you do? Then we went through the Archimede's principle. So in Archimede's principle, what is the main thing? The buoyant force is equal to
The velocity.
volume of the fluid displaced times density of the fluid displaced times gravity. And this is the buoyant force that is acting purely by the fluid on an object. The other force that can act on an object is the object's own weight. What is the equation for weight?
Mass times gravity.
mass times gravity, but isn't mass the same as volume times density? So we have volume of object times density of object times gravity. That's the same as weight. In fact, all the Archimedes principle problems you can solve by just using this. All Archimedes principle problems you can solve by just using this concept, this equation. Is that clear? Good. Now, before I go into numericals on Archimedes principle and all that, let me go over some more concepts that you will need to understand, because that's also related to pressure. One of them is called gauge pressure. Write down. What is gauge? Do you know? Have you seen a gauge?
Yes.
A pressure gauge?
Yes.
Where? Where have you seen a pressure gauge?
On like a gas can. Like an oxygen tank.
Okay, on an oxygen tank, yes, you see a gauge, yes. What else? Where else?
There one outside your house. Propane tank.
Okay, anything else?
Fire tank.
You don't see a gauge here. Do you see a gauge? I don't think there's a gauge on fire extinguishers.
Oh, a submarine.
Gauge. Have you used a gauge?
Probably.
By your own hand, have you used a gauge? Which one? Tire pressure. Tire pressure. Pressure gauge, like a little stick that you put there and it'll read something. That's a gauge. It reads the pressure. So what does the pressure gauge read?
Pressure.
The pressure, right? Okay, so if I take a tire gauge, hold it in my hands, what's the pressure here?
20.
What's the pressure? 14.7, right?
Yeah.
So does it read 14.7?
No.
No. What does it read?
0.
0. So what kind of gauge is that? I mean, you said the gauge should read the pressure. Now I'm saying, all right, if you're holding a pressure gauge right in your hands, the pressure right around the gauge is 14.7, but the gauge reads 0. So the pressure gauge does not read the pressure straight away. There is something else behind it. Yes?
It's because it always has that pressure on it no matter what, so it factors that in.
Yes, in one way, correct. So let's say this. Imagine someone slashed your tire with a knife and it's like torn into two, okay? The tire is flat. What's the pressure inside the tires?
14.7.
It's 14.7. Now you stick your gauge on it. What does it read?
0.
0. So what is that supposed to read? It reads the difference between inside and outside. That's what the pressure gauge does. So write down. Gauge pressure. Gauge pressure is the difference between the pressure and the atmospheric pressure. A gauge pressure is the difference between the actual pressure and the atmospheric pressure. So let's talk about a tire. So here's your tire. What's the pressure outside the tire?
14.7.
14.7 psi. And now you fill your air in the tires to 32 psi. If you fill tires with a pressure of 32 psi, that is the pressure gauge reading. What does the pressure gauge tell you? The difference between inside and
Outside.
So what is the actual inside pressure?
32 minus 14.7.
32 plus.
Plus.
Wait, what?
Yeah, it's the difference between here and here. That's recorded.
Oh, okay, yeah.
Make sense? So what does the gauge do? This is what the gauge does. As soon as you connect it to the tire, it looks inside the tire and says, okay, I see 46.7. What's outside? It's 14.7. Let me tell the difference.
That's why it's reading.
The pressure, like the gauge pressure is the pressure inside minus the pressure outside. Make sense now? Is that clear? It doesn't read the actual pressure. It reads the pressure difference. It doesn't read. That's why when someone slashes the tires, inside is 14.7, outside is 14.7, it reads 0. So what does the pressure gauge read? It only tells you how much more is the pressure inside compared to atmospheric. Did you get it? Yes, no? Good. Now suppose you drive this car after filling it with 32 psi. You're driving the same car up to a mountain top. So you're going up there. You drove up to the mountain top, where the pressure outside is 12.7. You know, as you go to a mountain top, the pressure on the top is less, right? It's only 12.7 psi. Now you stick your gauge in. What will it read? What will it read? Ben? What will that read? You stick the gauge over. You stuck the gauge over here, filled the tires up to 32 psi, drove the car up to the mountain top. You check the tires once again. How much will it read? 34. It reads 34 psi. And then you'll be wondering, like, no way. I know my gauge was reading 32 down here, and it's just barely a couple of hours, and now the pressure is 34, as if somebody inflated it. Why is it reading 34? Is because 46.7 is still the pressure inside. Because you're not removed any air, you're not put any extra air, so the pressure inside is definitely just that. Pressure outside is dropped. So now what's the difference from inside to outside is 34. So the gauge reads 34, making you think that that's impossible. It is possible. When the outside pressure changes, then the gauge will read differently. Yeah.
What happens when it's cold?
I'm going to come to it. I'm going to come to that. Now what happens when it is cold? Then changes are going to take place here. Because temperature affects the pressure also. When suppose it is hot. Now let's say you filled your tires to 32 psi. Okay? And now you're driving from here to Texas. Now in Texas is warmer. So here the temperature is 15 Fahrenheit. And then you go to Texas and it's like 70s and 80s. So if it is 70s and 80s over there, the temperature is higher. So what will happen to the inside atoms? Will they be moving faster? Yes, they'll be more agitated. And so what will happen is they'll keep bouncing on the tires with a higher speed, which means causing more pressure. So the same tires that you filled in with 46.7 psi inside pressure, when you go to Texas, even though the outside is 14.7 psi, the inside may shoot up to maybe 50.7 psi. The inside has gone up. Why? Just by temperature. You heated it up. Now what's the difference?
10 psi.
10?
Or not,
What?
no, sorry. I keep thinking
It's 50.7. Yeah.
35.
Yeah, it's going to be like
35.
30?
No. Yeah, 35.
It's going to be 36.
36. Oh, my bad.
It's going to be 36 psi.
Oh,
You fill in here at 32, you go there and discover that it is kind of overinflated.
yeah.
That's purely by the temperature. And the opposite is also true. The opposite is true. You fill it there at 32 psi, you drive up here, and because now it's getting cold, the pressure inside drops. So the gauge will now read like 28. Make sense? And then you'll be wondering, like, why is it deflated? It's not lost air, it's just the temperature difference. That's why it is a very important thing to periodically check the pressures. You know, just look at the tires, that will be enough. Just if you look at the tires, and if the tires are looking fine, straight. A little bit of, like compression will be there on the front tires because the engine is there. But if it is a little too much, then you should immediately check the tire pressures and fill it up or whatever you have to do.
So with a basketball, like if you, in the winter time, like you leave basketball out,
Mhm.
it'll deflate.
Yeah.
So is that kind of
It's the same thing. So why is the basketball appearing to be deflating? It's not because it's lost air, because the pressure inside dropped. When the pressure inside dropped, the atmospheric pressure is kind of pushing it in more. That's why it is kind of appearing deflated. You get it? So, what if, imagine, just imagine that suppose you are filling it to 32 psi, and for some strange reason, this atmospheric pressure increases, like goes on increasing. Let's say, for example, this whole car is placed in the chamber. The car is placed into a chamber, and you're pressurizing the air inside the chamber. You're pushing more and more air into the chamber and pressurizing the chamber. Let's say you made this pressure in the chamber. What is 30? The pressure is 46.7. You pressurize the chamber to 46.7. What will the gauge read?
0.
0. And what will be the looks of the tires? Flat. It will be absolutely flat, even though it's got 46.7 psi inside, but the outside is 46.7, so there's no difference. So nothing to hold it. Make sense? And so it will look like absolutely flat. So understand this concept of pressure itself. Gauge pressure is the difference between the inside and the outside. So think of that. Like if you buy a packet of chips from the grocery, you buy a packet of chips. The packet of chips is like that. Okay? What's the pressure inside and outside? 14.7. If it is not, if the outside is more than the inside, then what would have happened to the packet? It will compress. What if the pressure inside was higher than the outside? Then it will like blow up like that, right? So the pressure inside and outside are exactly balanced perfectly. And there is some locked air inside. Now what if the pressure of the atmosphere decreases? Or let's say you're taking this packet of chips in a plane, all right? You're taking it into a plane and you're leaving it right in front of you, and you keep watching the chips packet. As the plane takes off, there is changes of pressures taking place, right? The pressure outside is lower than the pressure inside. So what happens is, if the cabin pressure drops for some reason, what will happen to the packet of chips? If the cabin pressure drops, it'll swell up. So if the packet of chips is swelling up, you can understand, oh, there's something wrong with the pressure. It is losing some pressure. Do you understand? So if it's a properly maintained plane with the correct pressure level, then the packet of chips will look exactly the same down there or higher up. So very clear indication of that. Yeah, just looking at it. So if you buy a helium balloon and all that, and it's kind of deflated, it is sinking instead of rising. What you can do is just like warm it up, heat it up. But you have to be careful. You can't just take it to a flame and heat it up. It's helium, so it can be problematic. So you don't want to burn it, but instead just heat it up. All right. So wherever you have the hot air coming from the vent, just take it there and just kind of roast it. So after some time, you'll see that it is swelling up, and you release it, it wants to go up. You get it? Because it's swollen up, it gets the same buoyant force as before, so it's going up. But when it stays there, it gets colder and colder and colder, and so loses the pressure inside, and then finally starts sinking again. All right, so you get an idea of the pressures, right? Atmospheric pressure. What is atmospheric pressure?
pressure of the atmosphere?
Yeah, pressure of the atmosphere. And how is it measured, or how is it recorded? It is using an instrument called barometer. Write all the stuff down. A barometer is an instrument that reads the atmospheric pressure. Now there are two kinds of barometers. There are two kinds mainly two types of barometers. One is an aneroid barometer, which is analog. Aneroid barometer. Have you seen an aneroid barometer where there's a pointer that goes like that? Yes? Have you seen one like this? That's a barometer. There's a barometer. That's an aneroid barometer. Broken one, of course. That's a barometer. There's a dial where the pressure changes. The dial is supposed to move. And that's called aneroid barometer. And how is the construction normally done is this. It's like a container with a baffle kind of lid. It's a flexible lid. Make sense, Ben?
Mm-hmm.
It's a lid that is kind of can move up and down. If you push it, it'll move down. If you pull it up, it'll come out. That's the sort of thing. It's flexible. It's like your accordion, the bellows, right? Accordion, you can move it back and forth, so it's flexible. That sort of thing. Now, if something is connected here and it runs through a pulley, like that, and if you attach a pointer on the pulley, that becomes a barometer. What will happen if the atmospheric pressure increases? What will happen if the atmospheric pressure increases? What will happen to this thing? It will
Fall.
It will sink. When it sinks, it pulls the pulley, and the pointer goes that way. Make sense or not? Here, when this is pulled down, the pulley is rotated, so you get the pointer going like that, so it shows higher pressure. If the outside pressure drops, then the bellows move up, the diaphragm moves up, and it's going to show low. That's aneroid barometer. Yeah.
Can there ever be negative atmospheric pressure?
Nothing negative, because vacuum is zero.
So in vacuums, it can only be zero.
Vacuum is zero pressure, nothing is lower than that.
Have they like
What about a
discovered
black hole?
zero?
What's it again?
So they've never discovered anything lower than zero.
It's not possible because what causes pressure is particles.
So would it just be like a blank space?
That's zero.
But if they found something with like negative pressure,
No, nothing is there to apply negative pressure. See, the thing is, again, what is pressure? Pressure is created by atoms colliding, right? Atoms are moving and hitting the wall. So when this is the wall and this is the atom, because it has energy, that's why it's going and hitting the wall. When it hits the wall and bounces, there's a change of momentum, which causes a force on the wall, right? If you bounce something on the wall, there is a force applied on the wall, right? And force over area is pressure. That's how the pressure is created. That's how the pressure is created. Now, what if none of the particles are moving, like at absolute zero? Particles are not moving. Atoms are not moving. They're just still. Then what will happen? Will they come and collide?
no.
So pressure zero. Now, what if in vacuum? Suppose you have a container and it's vacuum inside. So what will happen? There's nothing to come and hit the wall and create the force. So no pressure. Now thinking of negative pressure, that's impossible.
So it would like disappear. Never mind.
I know you're trying to think of something which can pull, kind of create a negative pressure. No, pressure is zero. That's fine. That is possible, but not. Yeah, this is an aneroid barometer, and you can see those. Can you see those bellows here? There are a couple of them because that's how they work. So what happens when the pressure of the atmosphere increases? They get pushed, like they get compressed. When they get compressed, they're all connected by gears and levers. And because of that, of course, there are a lot of things missing here. It's supposed to be like a clock assembly. So when these things move, this thing will move, creating leverage, and that leverage will turn the gears, and finally will turn this dial. That's called aneroid barometer. Okay, stand. Take your notes in your hand. Stand and take your notes in your hand.
I'm okay.
No, you're not okay. You're not okay. All right. So that is one kind of barometer. This is aneroid barometer, which is analog type. There's another one which is using mercury. So mercury barometer. And what is this mercury barometer? It is a barometer made by using mercury, and I'll show you how it is constructed. I'll show you the construction of mercury. I'm not showing you, but imagine,
Is it a thermometer?
huh?
Or a thermometer?
Like a thermometer sort of thing. Imagine you have a 1 meter long test tube. Have you seen test tubes? Okay. Imagine it's 1 meter long, like
Do they
this.
make them that big?
Hmm?
They make them that big?
Oh, if it is needed, yes. So especially to make a barometer, you need to have it. Yeah. So it is a long tube, closed here, open here, like a test tube. Fill it fully with mercury. You understand what I'm doing? Fill the whole thing fully with mercury. The whole tube is full of mercury all the way to the top. And what do you do then is pinch the top. Just pinch the top so that this mercury is completely stuck inside. Not a single air molecule is inside. Then what you do is you invert the whole tube and put it into a container of mercury and release your thumb. So this is technically what you do. You have a dish of mercury. You have a dish of mercury and you put this tube upside down into it. You put the tube upside down, but it's already filled with mercury. So mercury is all the way to the top. Again, you take this test tube, fill it with mercury all the way to the top, then invert it and put it into this container and release. What will happen? What will happen to the mercury? Will it stay there?
It'll fall.
Will it fall all the way down?
Like it'll fill the dish. Maybe.
So the mercury is all the way here. Will it fall all the way down? Actually, what happens is it doesn't fall all the way down. It comes till here. It falls till there and stops. It cannot fall any further. It cannot fall any further. So let's find out why. Why is it stopping there? Why can't it just fall all the way to the bottom? Okay? So before you do that, I have to ask you questions. What's the pressure inside, just above this mercury? What's the pressure here?
14.14.
Created by what?
The atmosphere.
So what is inside here?
Nothing.
Nothing.
No.
Because it is full of mercury all the way to the top. And when the mercury came down, it was leaving behind what? Nothing. So what's the pressure?
Zero.
Pressure is zero there. In other words, that is vacuum. That is vacuum there. It's vacuum on the top. You can kind of simulate that one. If you take a straw, put it into water, and pinch the straw on the top, seal it, pull the straw out, you'll see the water is not falling all the way down. It comes down a bit, stays there. Noticed it? Only when you open it, then the whole water comes out. Otherwise, it will stay there. So pretty much like that. Mercury comes till here and stops. So let's discuss what's happening. So where is it going to stop normally? It stops normally at the 76 centimeter mark. From this mercury level, it is exactly 76 centimeters. That's normal standard pressure. That's a standard pressure, 76 centimeters. Now, tell me, if you go down from the top into mercury, what will happen to the pressure here? Will it be higher? As you go down in a fluid, will the pressure increase?
Yes.
According to which formula? If you go down any depth in a fluid, the pressure is supposed to increase because of the fluid. So the pressure is zero here, yes, it's zero, but now you're going into the liquid. So pressure is going to be higher, right? So what's going to be the pressure right here?
14.7.
Yes, we'll get to that one, but what is the pressure created by this fluid? So you can calculate the pressure here by using the equation H rho G. It's mercury.
What's the density of mercury?
I'll tell you that.
Oh, it's
13,600 is the density of mercury. 13,600 kilograms per meter cube. So find out, what is H?
76.
Yeah, we can't use centimeters, right? So convert it. So 0.76 times 13,600 times 9.81. Can you do this calculation and let me know how much you get?
Would be the 13,000.
That is the density of mercury. Mercury's density is 13,600. Find out how much. What, and in scientific notations.
I think I have it.
Got it?
1.01 times 10 to the fifth.
That's correct. It'll be 1.01 times 10 to the power of 5 Pascal. Isn't that the atmospheric pressure we have it? The 14.7 psi in Pascal is this. Check it out, you must have written it somewhere. The atmospheric pressure is 1.01 times 10 to the power of 5 Pascal, which is same as 14.7. Did you get it? Yeah, that is the atmospheric pressure. So, what's the pressure here?
14.7.
Which is the same as atmosphere. So, what is pushing from here is the outside atmosphere. What's pushing inside is the mercury. And they should balance. Because at the same level, the pressures are supposed to be the same. You get it? Yeah.
How could you turn the thing over, put your hand in mercury if it would hurt it?
Why not?
I thought mercury was harmful.
Yeah, why is mercury like
I've done it. It's not really harmful unless it gets to your bloodstream. Is that clear enough?
Yes.
Good. So if the atmospheric pressure decreases, what will happen is if this push is decreased, what will happen? You can't have high pressure here. So this level has to come down. Make sense?
Yes.
So the decrease in pressure outside, immediately this has to decrease, so it will come down. So the atmospheric pressure decreases, it won't be 76, but maybe 75, 74, 73. And if the atmospheric pressure increases, then it goes up higher. So just monitoring this level alone is enough for you to find out what the atmospheric pressure is. Okay, that is a mercury barometer. All right, let's now do problems from the textbook. Now page 275, can you turn to page 275? That's going to be a homework for you, but I'll get you started on it. Okay? I'll get you started with the homework. Page 275, sorry. Page 275. Page 275. And you see how I am working with it. And then you can understand how to do it. All right, put that away. Put that away. Put that away. Put that away. Now, before you do any problem, the first thing you should do for problem solving, whether it's a test or anything, is to read the problem and
Write a graph.
draw a diagram. Very important component. Draw a diagram. And on the diagram, you put all the information there and then start deducing what you can understand from there. Okay? So that is what you should be doing. That's what you should be doing when you actually read a question. So let me read this question and then guide you through it. A piece of metal weighs 50 newtons in air. It weighs 50 newtons in air. Now keep reading. 36 newtons in water. Why is it reading 36 newtons in water?
What? Sorry?
Why is it reading 36 newtons in water when it was reading 50 newtons in air?
Because it's a different. It's weighs
Less gravity.
No. But things weigh less in water. Doesn't it?
Why?
Why? Pressure. Pressure's
Water is higher density. Water is
Because there is a buoyant force acting on the object. That is why it is reading less. You understand that?
Yeah.
So what causes it to be less is the buoyant force. And then it says, and also it reads 41 newtons in an unknown liquid. And you're supposed to find the densities of the metal. And now you can answer this only if you're organized. Be it test or anything. Don't memorize any other equation. Your equations are right here. This is what you need and nothing else for solving such problems. So you can see that I'm not going to basically use anything else. I'm going to use that. But other than that, this is your equation. Alright, so it says over here, this is the drawing I'll draw. This is weighing 50 newtons. It weighs 50 newtons. Now the same thing underwater. It weighs 36 newtons. And the same thing in an unknown liquid. Weighs 41 newton. This is what is given to you. That's what is given to you. Now first let's find out what you can understand from this scenario. Alright, it was reading 50 newtons, right? So if I have a scale reading here, if I have a scale, that scale will read 50 newtons on the scale. And if I have this scale here, that scale will read
36.
So tell me, why did it lose the number? Why is it lower now? Because
Buoyant force.
it's a buoyant force. The buoyant force is pushing it up. The buoyant force is what's pushing it up. And what's buoyant force? It's the weight of the
Object.
fluid
Fluid.
displaced. Weight of the fluid displaced. You get it?
Yes.
Yeah. Before I get into the problem, let me tell you about the fluid displaced concept. Watch this. If that's a container, now this is, I don't know if I mentioned this earlier. Did I give you this?
Nope.
No. Okay, write it down. This is called a displacement container. Displacement container. Which means what? You pour water into it. You pour water till there. You can't take any more water. That's the maximum it can hold, right?
Yeah.
So suppose I actually put a block. If I take this block of steel or whatever, if I take a block of steel or something like that and put it on a scale, if I put it on a scale, it reads 20 newtons. That means in air it reads 20 newtons. When I take the same thing and put it in such a way that the block is now in water, what will happen as I put this in?
The water will rise.
Water will rise, and so what will happen to the water will come out from here? Let me collect that water in a beaker, and I'm placing that beaker on a scale. I'm placing the beaker on a scale. So when this thing went inside, some water comes out, right? What is this? That's the mass of the fluid displaced, or the weight of the fluid displaced. You get it? Suppose this scale reads 2.5 newtons. If this reads 2.5 newtons, what will be this reading?
17.5.
17.5 newtons. Does it make sense? Right? Because it is reading 17.5 newtons. Why? Because as soon as it went there, it experienced a buoyant force. And what's buoyant force equal to? Buoyant force is the weight of the fluid. Weight of the fluid displaced. That's why this is reading 2.5. That's the buoyant force. So it experiences 2.5. That's the buoyant force here. So what? See, the buoyant force is 2.5, and that's why the reading is less. So how do you know? How do you know how much the buoyant force is? Is by comparing the two.
You just subtract it from the one in air.
Exactly. So weight of the object. What's the equation for it?
Mass times or volume of object
See this?
times.
So I can write 50 is equal to volume of object times density of object times gravity. Is that okay?
Yes.
Now what's the buoyant force here? What's the buoyant force here?
24. 14.
14. The buoyant force is 14 newtons. What's the buoyant force formula? What's the buoyant force formula? Volume of the fluid displaced, which is volume of the water displaced, times density of the water displaced, times. Is that clear? What do you know about the volume of the water displaced and the volume of the object? Are they the same? The volume of the water displaced, will it be the same as the volume of the object itself?
No.
Yes.
Yes.
Because it's fully inside. When it's fully inside, the volume of the object and the volume of the water pushed out is exactly the same. So therefore, I can write this as 14 equal to VO rho W G. You understand why I switched volume of water is the volume of the object? Because how much water is displaced is exactly the same volume. This is VO. That is VO. That means the amount of fluid displaced is also same. Alright, now we have two equations. Watch this. 50 is equal to VO rho O G. 14 is equal to VO rho W G. Two equations.
Yeah.
Divide the two equations. Just divide them.
Like that.
So what will cancel?
VO.
And
G.
now it becomes a very simple equation. You have 50 over 14 is equal to rho O over rho W, which is the density of water. What's the density of water? 1000. So it's 1000. So what is rho O? Cross multiply. Get it. 50,000 divided by 14, which is answer. Punch the buttons, quick. Everyone should have calculated. Not maybe. Tell me the exact.
3,571.43.
Say it again.
3,571.43.
Okay. This is a density in kilogram per meter cube. Just keep, and I've used everything in SI units. So, you get that clear? Is that clear? Now let's go on to the next one. What's the buoyant force here? So the first question here is asking you, what is the density of the metal? We got the density of the metal.
9.
So that is 9. And so how do you write the equation? 9 is equal to volume of the liquid displaced times density of the liquid displaced times gravity. So 9, can I write volume of liquid displaced as same as volume of object? Same thing? Write it down somewhere. Volume of the liquid displaced is the volume of the object if it is fully submerged. If it is floating, that's a totally different thing. If it's fully submerged, then this is true. Density of liquid, gravity. Now I'm going to use this equation and that equation. This one and that one. Or this one and that one. Use any two. So I'm going to use 14 is equals to VO, rho W is 1000 times G, and divided by 9 equal to VO, rho L, G. What do you get then? When you divide both the equations, VO is out, G is out. Can you find the density of the liquid? Density of the liquid is equal to Yeah. If you're not having calculators, in spite of my telling you so many times, something else has to be done. 642 kilogram per meter cube. Is that clear?
Would you round?
Yeah, once you come to this point, then you can round it. You can round it to 3 sig figs. Even this one, you can write it as. You can round it off finally to 3 sig figs. Because I think all the stuff that's given to you is all in 3 sig figs. This is given as 50.0 newtons. That is 36.0 newtons. 41.0 newtons. So keep 3 sig figs. That's fine. Even otherwise, keeping 3 sig figs is a decent representation. Is that clear? If I ask you what's the volume of the object, what do you do? Again, turn to one of these equations. I want the volume of the object. You know this 50. I want you to find this. Do you know this?
Yes.
Yes.
Yeah.
Mass times.
Gravity, 9.81. So you can find the volume. Is that clear? Yes? Good. I'm doing another one for you so that you will have an idea how to do the rest of it. Again, do not memorize any of these equations that is mentioned in the textbook. That won't help you. That won't help you to solve problems. Don't like, okay, I have a magic equation I can apply. No. Think about it, draw, and then get it. Now, the next one is a 2.8 kilogram rectangular air mattress is 2 meters long, 0.5 meters wide, and 0.1 meters thick. What mass can it support in water before sinking? So here is the water, and the mattress is actually there. It is air mattress, but it weighs what? 2.8 kilograms, right? So it won't be completely out of the water, right? It'll be little into the water. You see it? So what is making this float right now? What are the forces?
Atmosphere.
What are the forces acting?
Buoyant force and weight.
Yeah, the weight is acting downward, which is actually the 2.8 kilograms times g, right? So 2.8 g, that's the weight. What's the other force?
Buoyant.
Which is offered by what? By that fluid. The weight of this much fluid, that's the buoyant force. And what do you know about those two forces right now? They are equal. But the question is saying, what mass can it support in water before sinking? So, can I put some mass on top and let this air mattress still float? Think about it practically. Think about it practically. You know, you have an air mattress floating in your pool. Can you put something on top of the air mattress and still have it float?
Yes.
Yeah. Question is asking you, how much maximum mass can you put on top before it like fully submerges? Which means this is a new situation. The whole mattress is inside. The whole mattress is inside, and this mass is put on top. If you put any more, everything is going to go down, right? But this is the maximum. So maximum means you got almost the entire mattress inside. Not almost, everything's inside. Now tell me, what are the forces acting? What are all the downward forces?
Weight and mass.
One is because of this, and one is because of this, and the weight downwards, right? So what's the total mass?
2.8 m.
M plus 2.8. That's the total mass. Times gravity. That's the total weight downward. What's the only force upward? Buoyant force offered by the fluid displaced. The buoyant force. And they are equal. What's the equation of buoyant force?
It's
VF,
yeah.
volume of the object, or volume of the object, okay, VF, rho F, G. That's equal to M plus 2.8 G. You know how to find the volume of the object, right? And then density of the fluid is water.